Well, good afternoon. And you can't find a better day with sunny sky in November. Believe it or not, it is the 1st of November. And we are thankful for the good weather. And our thoughts go for sandy people on the other side of the continent where they have some troubles. So we just count our blessings here and pray for them and bring them in keep them in our thoughts. Welcome to this session, special session of this symposium, a futuristic look through ancient lenses. Now, if you are in a class with Mr. Linton, you are obliged to look into the skies, kind of. You have to because this is your work, your study, your specialty. But guess what? We, the 21st century guys and girls, mostly lost the glory of looking to the skies and have our thoughts just go and float like this. I wish many more would do this and look at the moon, look at the stars, and so forth. Well, before I introduce our distinguished speaker today, I want to thank John Luby and give him a hand, please. Now, if you see microphones and media services and others, usually you don't see the people behind the screens and the curtains. We want to acknowledge him, and Arlene here will give him this certificate of appreciation, working behind the scenes, but always seen.
Well, thank you so much. Thank you for
Thank you. Thank you. Another thank you goes to Bev. She faithfully documents in picture, artistic picture, all this symposium and other stuff. You have seen her. Maybe in your graduation you'll see her also. She'll take your photos as well. So thanks, Bev. Thanks to Wes, also documenting in video. So thanks to all the media. Please give them a hand. Without this, we couldn't document it. Well, he tries to bring the skies down to earth. And he is a down-to-earth person. I mean, I've never seen such a pleasant person to talk to and discuss things and work with over the emails for a long time. And then when I met the person, it was a pleasant surprise. So thank you very much for accepting to come and speak with us.
Thank you, Wafik. So, I
You
should
are
start?
all
Okay,
yours.
very good.
All yours.
Thank you.
Thank you.
Well, let's get going. I've got title slide here with a couple of graphics. A year ago, the title was Bringing the Sky Down to Earth. That was Egyptian astronomy. Here we're doing it a little bit differently. Astronomy in ancient Greece, that's not where it started. That's not where we began seeing astronomy. But I think that's where it became a science. Or maybe not exactly a science as we define it today. There weren't all the elements of science going on then, but many aspects were created, invented in ancient Greece. On the the left side of the screen, you have a depiction of the Pythagorean universe, the central fire, the hearth of the universe, the home of Zeus. It's been called all of those. I will talk about that a bit later. We can't see it because there's a counter Earth there between us and the central fire. That was one of the models. Hipparchus, a person that I also have not spoken of in the astronomy class, or classes this semester, is probably regarded as the greatest astronomer of antiquity. You'll hear some about him yet later in this in the semester, those of you who are in my class. You see him there actually observing with an instrument known as a quadrant, astrolabe perhaps, measuring perhaps the altitude of a star, perhaps measuring something else in the sky. So Greece is a long ways away. So on our way to Greece, let's stop off in Florence. And we did so 2 years ago. I didn't know in advance that you were going to be doing this, but met my namesake, hobnobbed with some ancient astronomers, and had a feeling, as I've looked back through my slides, I've had a feeling that maybe I really was in Greece. there was statuary. It was just gorgeous statues. Pegasus, the winged horse. I've had one group out that I've had a chance to show that to. That star pattern, at least, not the flying horse itself. You have to use your imagination that that's what it outlines in the sky. But there it is. Nice sculpture. And if you look carefully, right up here, you'll see a baby flying off in the distance. Baby winged horse. So there was also Poseidon in Florence. And what else did we have? Benvenuto Cellini's bronze of Perseus and the head of Medusa. And we have Perseus the warrior in the sky close to Cassiopeia, and also to Andromeda and Pegasus. Reminders of the Trojan War. That was probably fought somewhere, Lee, can you give me a date? Maybe 1200 BC?
There was no actual Trojan War.
There was no actual Trojan War. I read Homer's...
Circa 1200.
Circa 1200. Okay. But certainly reminders. I thought that was evidence in behalf of that. After Florence, moving a little closer to Greece, went to the other side of Italy, and on the Grand Canal in Venice, looking over at St. Mark's Cathedral. The cathedral right here, this building, the Campanile, or bell tower. And we'll go up that. It's quite a view from up there. We'll go up there in a moment. You have this building that we're going to take a much closer look at here shortly. This is a building with, you know, a clock in it. Very special clock that we'll take a look at. Let's go to the top. And when we go to the top, we find Galileo again. He has been here, and he was there. Well, this is 2010 when I was there, so just over 400 years ago. And it was August 21st that he was there, and what was he doing? He was showing off the new telescope, a telescope that he had built, to the leader of Venice. And he's trying to sell it and sell himself as the maker of the telescope. He did not invent the telescope. He heard about it, and with the glassworks near Venice at Murano Island, he was able to get glass ground to his specifications and to make telescopes. He made some money doing that. He got some influence and a great reputation. 1609, August. And what would you use a telescope from up there for? And it's not looking very high in the sky. In fact, I don't think he should really be looking up at all, because when you look out, you're looking down at the red tile roofs of Venice, and off in the distance, if you're looking the right direction, you're looking towards the Adriatic Sea. Maybe there's some enemy ships coming in. You can see those. You can use this for defense, early warning device. And that could be what it was used for, what he was trying to sell it for in August. What things changed in the next few months. Now, look again at this building that I've called your attention to before. This building houses a clock right here, and a couple of probably bronze folks on the roof there to ring a bell. But my attention was drawn to the clock. And I went down there and looked up from ground level, and the clock is really very beautiful. It was constructed 110 years before Galileo showed his telescope to the Doge. It was finished 110 years earlier. Looking carefully at the ground level, you can see some signs in the windows. So we take our culture, our own culture around the world as well. It's spread. There's Bar Americano in those two windows down there. Up close, what you see is something, again, from Greece. This is the culmination. This is represented there, the culmination of science, of astronomy science, the best science in ancient Greece. Put together in about 140 AD, I believe. This is a 24-hour clock. Of course, the numbers in Roman numerals around the edge. And the pointer, there's only one pointer, not a minute hand, just a hand, I guess, a pointer. And that's towards the number 16. It's 16 o'clock, which I guess we should say 4 o'clock in the afternoon. And that is the sun in the sky. In the center is an immobile Earth. Earth is not moving. It's stationary. And this was the cosmos. This was the universe to the Greeks. Not to all, but to most. And by the end of the run of science in Greece, with Claudius Ptolemy in about 140 AD, he put together this model in its best form. Earth in the middle, we've got the moon here, not in the same direction as the sun. Off a little bit to the left, its phase is shown as a thin crescent. We've got what here along the edge inside of the hours? What's that? Constellations of the zodiac. Is the constellation through which the sun moves in the course of the year. And if you watch this, maybe you look at it again after taking a gondola ride, which we did. The time has changed. Earth's still there. The hour hand or the hand has moved. But so have the constellations. The sun is moving with the constellations across the sky. So has the moon. It's moved from over here up this way. Everything's moving together across the sky. If you came back a day later, well, let's just go back and look at it a moment before, or a couple of hours before, 2.5 hours before, and again here you can see the moon and the sun and the constellations moving, but Earth is immobile. So if you came back 24 hours later, the sun would be up there again, but what the biggest change you would have noticed was the moon moving about 13 degrees this way. If you look carefully or looked after a few days, you would begin to notice that the sun is moving with respect to these constellations, these signs of the zodiac. It's slowly moving into Gemini and through Gemini and then through Cancer at about 1 degree per day. These are elements of the geocentric model, the Ptolemaic model of the heavens. And when Galileo was with the Doge, the top of that tower, just a couple of 100 feet away and a couple of 100 feet up, this clock was there. Been there 110 years. But when the clock was built, something else was happening in Europe. Nicholas Copernicus was 26 years old. Eventually, he would put forward the heliocentric model, the sun at the center. And the phrase revolution, the term revolution, would be used in a new way. Something was cooking. Now, within 5 months of Galileo's visit to the top of the tower, he had gotten the idea that if he stepped up the magnification from 5 or 10 power up to 30 power and turned it skyward, he could use it as a tool of scientific investigation. I wonder what the sky looks like. Might have been what he was asking himself. And he got some surprises, some amazing surprises, and he shared them with the world in a magnificent book, The Starry Messenger, Sidereus Nuncis, in 1610, published fairly early in 1610, describing his observations. This book was so amazing, had so many surprises about life and about the universe around everybody, that it was, within 5 years, it had been translated into Chinese, among many other languages. What he saw challenged the geocentric theory. Some of the things that he saw were just not consistent with the geocentric theory. This is a new tool of technology. Never been around before, never been used in astronomy before, and now we see that what the Greeks have put together may not be correct. And it set in motion so many things. 24 years later, he was brought before the Inquisition and ultimately convicted of heresy at the direction of the Pope, I believe Pope Urban VIII, sentenced to house arrest for the remainder of his life. But these observations with the telescope ignited the first golden age of astronomy, during which a new tool of technology was brought into play and new ways to understand the cosmos were introduced. Now, we're in a second golden age right now. We have only recently been able to get beyond the atmosphere with our, some of us, and also with our technology and the Hubble Space Telescope, other telescopes, other probes going to other worlds. We are just learning things about in astronomy at such an amazing rate. I would think that no Greek or Italian astronomer ever dreamed of such wonders, knowing such things. But we could not know those things without having learned what we learned in ancient Greece. And it happened about 26 centuries ago in a small city on the eastern coast of the Mediterranean, where we begin to approach nature in a different way. Well, none of us were there, of course, although you might have doubts about me. But it's part of our heritage. The city was Miletus. Don't hear about Miletus all that much. It was a commercial town. It had was a port. It had carried on commerce with Babylonia, Egypt. There were ideas that came into this town. It was a noteworthy town in other ways. It was a colonizer. They set up 90 separate colonies. At least that many were identified in some of the history books. And it played a role. What took place there played a role in the next few centuries, turning science into what has been called the greatest invention of all time. Greatest invention by human beings. I think you could probably argue it. Maybe there's some other things that you should consider, but it is our way of finding out about the world. And upon that understanding, we build technology. We make our lives, hopefully, better. It doesn't always work that way, but over time, that's what we hope. That's what we've come to see. For peoples of that era and before, the sky was common knowledge. You didn't have a watch on your hand or a cell phone to check the time. You didn't have a calendar on the wall, probably. But you could glance at the sky. And a quick look in the sky, a glance at the eastern horizon at dawn, seeing what constellation was there would tell you what time of year it was. And it was mentioned in literature, I'm sure much of it has been lost, but in Odysseus, or in the Odyssey, one of the portions, in one part of the story, I believe it is Calypso, who talks to Odysseus and gives him instructions on how to return to Ithaca. It's when the winds are bagged up and only the west wind is allowed to blow. And he says, well, how do I steer? And he's told, well, keep the Great Bear on your left. That's north. And sail towards the rising point of the Pleiades, the Seven Sisters. And that would send him on a course due east. Wouldn't work today, but it did back then. I'll hope to mention something about that later on. Probably best if I mention it now. We've had a slow wobbling of the Earth's axis, what we call precession, that changes where the Pleiades is in the sky. It's no longer on the celestial equator. It no longer rises due east. It's quite a bit north of that. And if you sailed towards it right now, it would probably be about 25 degrees north of east. So don't follow the instructions. Don't use Odysseus or the Odyssey for finding directions in the Mediterranean. Probably GPS would be a little better these days. Chinese and Babylonian astronomy come up periodically. These go back earlier than the 6th century before the Common Era. There are written records that are around from at least about 750 BC for the Babylonians, and I'm not sure how much further back for the Chinese, but these were major institutions in both countries. both civilizations. Astronomy was. The astronomers were charged with doing certain things. In China, it was mostly to keep track of the calendar. There were certain rituals that had to be carried on. And of course, to the extent that astronomy is tied in with agriculture and needing to know when to plant and do other things associated with agriculture, that was important. In Babylonia, they had different motivation. They seemed to be very interested in finding correlations between things going on in the sky and things happening down here. A king dying. Well, if that's all in any way associated with what's going on in the heavens, I would imagine the next king is going to want to know, can I get some advance notice of this? Get some warnings. Looking for correlations. Maybe a king dies when there's an eclipse seen, or maybe when a comet is observed, or maybe when Jupiter is in a certain constellation. Well, observations were made, correlations perhaps were found. Sometimes they probably thought there were cause and effect relationships, but correlations, nevertheless, sometimes were there. In the pattern, or in the data for the Babylonian astronomy, we have centuries of data on solar eclipses. You can go back through those, and if you do carefully, you'll start to see that there is a pattern. Not for every one, but it turns out they eventually found that every 18 years, 11 1/3 days, there's a solar eclipse. The Saros cycle. But in both places, they did not have a conceptual understanding of how Earth fit in with the cosmos, how it was all arranged, the geometrical arrangement. This was an invention of the Greeks. To the Babylonians, they kept numbers, they kept dates. And you could just not even think about how they were related geometrically, just look at the dates for patterns. Carlo Rovelli, and I'm going to show a slide of this, but I was handed this very recently in the last few minutes. The first scientist, Anaximander and his legacy, Carlo Rovelli. An excellent book. I read it this summer, stumbled across it, and it's not very long, but it's full of great stuff about a man that Rovelli feels was the first true scientist. Others earlier times have suggested that Anaximander's predecessor, Thales, was the first. But his comment, Rovelli's comment, at a certain point in humanity's history, the idea came into being that it was possible to understand these phenomena: atmospheric, geological, astronomical. Their interrelation, causes, and connections without recourse to the caprices of gods. This immense turning point took place in Greek thought of the 6th century before the Common Era, and it is consistently attributed to Anaximander in all of the ancient texts. Aristotle talked about Anaximander. Others did too. Unfortunately, we have, I think, close to 30 words of his that actually come down to us. It's sad, but there's still hope for finding one of his books. But we're going to learn a few things about him today, I think. That's what the cover of the book looks like. If you didn't see me hold it up there, Pliny, historian, remarks that it is said that Anaximander of Miletus first opened the doors of nature. He stopped asking, which god threw the thunderbolt that struck my friend Joe, or that scared the bejeebers out of me. Stop asking questions like that. Started looking for other things. Rovelli comments that when he opened the doors of nature, Anaximander ignited a conflict between two profoundly different ways of thinking. They're still around. On one hand, there was the dominant mythical and religious way of thinking based in large measure on the existence of certainties that by their very nature could not be called into question. And putting it in modern terms, if a person believes in the Bible, the Quran, the Torah, and believes that many individuals who believe in one of these texts will believe in the inerrancy of the words that are written there. Cannot be called into question. Observational data doesn't make any difference. On the other hand, there was a new way of looking at the world based on curiosity, rejection of certainties and change. Rejection of certainties, comma, and also based on change. Okay. This conflict has run through the history of Western civilization century after century with alternating outcomes. It's still an open question. The clash, which we see strengthening today, is measured in millennia rather than centuries, in Ravelli's view. It does not yet change very quickly. Another Anaximander biographer, Dick Couprie, says an astounding thing, that based on what we know about Anaximander, we are convinced that he was one of the greatest minds that has ever lived. And he does not hesitate to put him on a par with Newton. These were people like us, human beings, approaching the world, but without a foundation of understanding, without the principles of physics or astronomy or of any science, really. Trying to learn those basics that, well, we think they're basic today. Anaximander is said to have drawn the first map. I don't know. I wouldn't be surprised if others were drawn but lost. But he drew an earlier map than this, and Hecataeus, I believe, of Miletus, who overlapped in his lifetime with Anaximander, drew this one. This is better than the one that I saw for Anaximander, and so I included this one. You see some cities here that are worth noting. Babylon, Memphis and Thebes in Egypt, Miletus, of course, Athens. Sparta is not shown. Syracuse, a Greek outpost in Sicily, and Carthage that would have some interesting history coming up. Rome is not shown. Venice is not shown, but there is an Etruscan city or village outpost, I believe, very close to where Venice is right now. And Florence, by the way, is over here. And the known world, the known land, is surrounded by ocean. We know more of the world today. Oh, another city that is not shown, but will become important is right here. Will be right here. It's Alexandria. More details of the Eastern Mediterranean, and Miletus is right here. Very close to this, but not mentioned, is Samos or Samos, where a couple of astronomers are from. It's just off the coast, I think an island. And at Anaximander's birth, humans have been living in cities for at least 10,000 years. The great kingdom of Egypt had been in existence for 26 centuries, and we're looking back 26 centuries. So it was interesting. Thales, the predecessor to Anaximander, visited Egypt and asked, how tall is that pyramid? And he says, why ask us? We don't know. How do we measure that? You think we were around when it was built? I'm paraphrasing, of course. And he figured out a way to figure out how tall it was. He waited until his shadow length was the same as his height and measured the length of the shadow of the pyramid. I imagine that was included in future tours. You know how tall this is? Babylon, with 200,000 inhabitants, was the largest city in the world and had been for centuries. And the Babylonians, by this time, had developed the concepts, many concepts of the sky, and that Ravelli points out are pretty much included in grade school curriculum. We teach them to our 7-year-olds. That's what we mean by real advances back then. Thales is commonly referred to as the first scientist. Anaximander studied under him. He's said to have predicted the solar eclipse, and from this we think, a lot of people think that he had access to the Babylonian tables of data. It's hard to see how he could have predicted an eclipse otherwise. And certainly with the commercial connections with Babylonia, that was possible for him to have had access to it. Believed the universe came from water, that water was the common element of the universe. He introduced deductive logic. There are several theorems that he is responsible for, theorems in geometry. He used geometry. I mentioned finding the height of the pyramid, but also from 2 different points on the shore, you can measure angles and determine the distance to a ship. That could be very useful to you. He held that the earth is flat and floats in water. You know, a child asks you, why is the sky blue? Or how far is that town you're talking about? We took our grandson to the beach in South Carolina this summer, and he was astounded how far a drive it was. But the world is bigger still. We come into the world with lots of questions, develop more. This is at a time when they were answering some of the basic ones, or trying to. Why the emphasis on Anaximander if Thales is thought of in the way that I indicated here? Part of the reason is that Ravelli is looking at it as a scientist and not as a historian. Just how do these ideas that Anaximander is supposed to have introduced, what did they take? What was the conceptual leap from attributing actions to the gods to explaining the phenomena in the way that he did? And he feels that they are extraordinarily significant. They're far more wide-ranging than Thales, although Thales was very interested in lots of different things. From meteorology, where he had a very good understanding, the water evaporates and turns to rain eventually. Wind blows and it moves the clouds around. Biology, biological evolution, he is most noted for that in modern science. Geology and astronomy as well. Anaximander was a student of Thales, but did not feel compelled to support his worldview, and this Ravelli thinks is an important aspect of science. If you can think of think of a leader in a religion and a follower. The follower doesn't just turn around and, after the leader has perhaps passed away, and start coming up with, or start suggesting that, well, the leader wasn't right on everything. Let's go off in this direction. Well, that sort of loyalty in the scientific realm is possible too. If I'm a student under Thales, boy, he was a smart guy, and I'm going to stick with his ideas. No, that wasn't what happened. Every idea, even if it was an idea held by a professor that you studied under, and you felt very obliged to that professor, you'll knock that off the pedestal very quickly if you find good reason to. Observational, experimental evidence, go in another direction. A very important aspect of science that we see here first with Anaximander, at least Ravelli, is identifying this as a very important step. Now, one of the things that Anaximander did before this time, of course, we had concepts of the world being held up by something. We didn't have an idea of gravity and how it works, nothing like that at all. And you're just on one side of the world. We don't go to the other side and see that there are people standing on that side, pulled towards the center. But the Bible talks about the pillars of creation holding earth up. We have other cultures talking about turtles and beings, and we got Atlas, I believe, carrying around the world. But Anaximander looks at the stars in the sky, looks towards the northern horizon, sees the stars, some of them all above the horizon, going around and around. You can see them do that in the night. There's nothing obstructing them. And other stars rising over here and moving across the sky and coming down and hitting the horizon, and then they must go below the horizon and then reemerge. Can't be anything in the way down there. We are floating in the void. And Ravelli thinks this is a tremendous step. And Anaximander was asked, "Oh, why don't we fall?" And Anaximander says, "I can see no reason why we should. I don't see the mechanism that would cause us to fall." This is a depiction of his worldview. The world is a cylinder. Doesn't sound very, very right. We know it's not right. The world's a cylinder. You've got basically that map that I was showing you before, right up at the top of this. The height of the cylinder, he says, is about a third of the distance across. And there's air and fire and the sun. I'm not going to go into it very much, but it's a cylinder. We think of the Earth as what? What shape? Hope you know. It's a sphere, we think. You know, a sphere could impress us, I guess. They thought if he'd come up with a sphere. But here's the first person to put any kind of curvature into the Earth. The next step is a sphere. But that's not right either. The Earth is not a perfect sphere. The distance through the center from pole to pole is less than from equator across the equator. It's not a perfect sphere. It's an oblate spheroid. And then you start taking a look at the mountains sticking out, you end up with something that is vaguely reminiscent, if you exaggerate, it's of a pear shape. So should we be critical of later individuals who said the world is a sphere? No, everybody makes progress. Science makes progress step by step, building on what was known before. And this was a tremendous step to add some curvature to the Earth. This person said something like a squared plus b squared equals c squared. Pythagoras. And the Pythagorean hearth of the universe. I won't spend much time on this other than to say what I said at the outset, that he has the sun going around the central fire. He has the Earth going around, and it's not quite a, well, it's not a geocentric system, it's not a heliocentric system. But he's looking for a way to explain geometrically the arrangement of these objects, some of them in the sky and another one in the Earth. What's their arrangement? How do they move? Pythagoras of Samos, I will say that's the pronunciation, lived in the 6th century BC also, BCE, held that the Earth is spherical, probably the first person to suggest that, and what he saw was that the ships sailing away from shore disappeared hull first and then later the sail. And it's not just the ships. If you're out sailing and you find a Greek island off in the distance, what do you see first? You see the tops of the mountains. They're usually volcanic, or at least have some vertical relief. You see the tops of the mountains, then you get closer, and those are in view, but also lower down on the mountains. First to suggest that the sun, moon, and planets could be described by numbers and mathematical precision. And he's apparently the first to suggest, at least in Greece, that the morning star and the evening star are one and the same, the planet Venus. Plato introduces us to the idea that the heavens must be perfect. And I don't know that, maybe it was felt that way before, but now it's got a geometrical sense to it. The only permissible path must be the circle, the perfect shape, flat shape, plane shape figure. And three-dimensional bodies must be spheres. Changes do not occur in the heavens. You can't improve upon perfection, so it must be timeless and eternal. Comets and meteors must be things going on in the atmosphere somehow. We still think that of meteors. We do not think that of comets anymore. Heavens are composed of a perfect material, invisible crystalline material, better than diamond, I suspect. Quintessence or ether. Aristotle, student of Plato. I could spend a lot of time talking about him. I am going to resist doing that. I think he's been talked about a lot in a lot of other presentations. He gives us the geocentric theory, the Earth in the middle, the moon going around, and so on, the sun out past Mercury and Venus. These two planets are called inferior planets. And then there is a sphere of stars out here, and then invisible to us is the sphere of the prime mover. We still use in astronomy courses models of the celestial sphere. Now we've got an Earth in here that's much too big. Should be just a little speck inside, but it helps us to try to see where we are and what we might see in the sky if we've got the stars in a reasonable size and we can pick out landforms on the Earth. And that was, in a sense, the limit of the cosmos to the Greeks. Limit of the universe, a bit past Saturn. In truth, we should look at it as a three-dimensional system and not just circles. What Aristotle was suggesting was that there were these spheres, and there was a sphere for each planet, and the planet was on a sphere, and there was some kind of mechanism that involved these. And I jump way ahead. There's a lot of individuals who contributed in between. I'm skipping them, skipping Eudoxus, skipping Apollonius, and a few others who contributed to this. They added more spheres. Eudoxus, a student of Plato, actually comes up with 27 spheres, all made of the perfect crystalline material, each one for an object and some extras to help them move properly. And later, individuals expanded to at least 55 spheres. And I would not have wanted to bring that model in if one existed. Now, Claudius Ptolemy looks back. These years are not BCE, these are AD. He looks back, he does a great deal of astronomy himself, observations, but he also takes the Babylonian observations and the ideas of previous Greeks, and he puts them together in the best model he can to explain the observed motions of the planets, of the moving bodies in the sky, the stars as well. The stars aren't all that much of a problem, but because all you need is a sphere, and you just rotate it, or let nature rotate it, or the gods rotate it. The introduction here, something included by Ptolemy, is that, yes, the sun is out here past Mercury and Venus, but Mercury and Venus are never seen far away from the sun in the sky. We see it tomorrow morning. If it's clear, you'll see it in the eastern sky before the sun comes up. Very bright planet. Last year, we saw it in the west after the sun had gone down. But angular, speaking of angle, never more than about 42 degrees away in the sky from the sun. So he decided that the only way that was going to work was if he forced Mercury and Venus to the center of their motion to lie along a line joining the sun to the Earth. And the planets themselves are moving on epicycles, circles, secondary circles are introduced here. And each of the planets has one. It takes Venus from one side of the sun to the other, Mercury too. But the superior planets, the planets that today we think of as farther from the sun than we are, these are planets that have epicycles, but they're not constrained in the Ptolemaic system to be close to the sun at all. So they can get on the opposite side of the sky. But what happens for all the planets is that when they're on the inside of the epicycle, they're going in the opposite direction relative to the direction the center of the epicycle is going. Each center, an imaginary point, is moving in a circle on a deferent around the Earth. And the combination of this leads to the planet backing up amongst the stars. Why would he do this? Because that's what they're seen to do. Occasionally, they change direction. Now, here is probably a simulated version of a view of Mars, photographed at 1 week intervals, let's say, moving with respect to the stars, moving in front of the background stars, still moving across the sky from east to west in the night, but not being close to the same point amongst the stars. A week later, here, 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 and then it slows down, and then it starts going backwards, and then it stops again and starts going forward again. Today, we understand this as we're going around the sun. Mars is going around the sun, and we pass it up, so it looks to us from our moving vantage point that it's going backwards. But if you put the Earth in the center, that's not going to work. You got to come up with another system, and that's the system that Ptolemy and others before him came up with. And this worked very nicely qualitatively, but Ptolemy was really trying to put some numbers into this, put mathematics to this, and it became necessary to add extra circles. And we've talked about this in astronomy class. Remove Mars and put there an imaginary point that has another circle going around it, so that Mars is moving in a circle around an imaginary point that is moving around another imaginary point that is moving around the Earth. And you've got some more numbers you can adjust, another circle of size and speed that you can adjust. And eventually there were 28 circles, and that was just for Mars. It was a cumbersome model, but it worked better than anything anybody had ever had before, and Ptolemy was proud of it, very proud of it. It had all been done with circles and spheres, and of course the heavens have to be done with circles and spheres because we know, it just seems right, that the heavens are perfect. Earth was a sphere, did not move in any way. That was part of the accepted view. Earth was a sphere, not that it was a flat place. And the celestial sphere marked the limits of the cosmos only slightly further than Saturn. The Ptolemaic system went unchallenged, virtually unchallenged, for 14 centuries. In that sense, it would have to be the most successful scientific theory ever. But it was wrong. But we're coming to grips with being wrong. If you are in science, that's what you learn. Yeah, I've got an understanding, but I've got this little bit of uncertainty out here about just how right I am about that. So I'm always testing if I'm in research, and that's my field. This model came to be accepted by the Roman Catholic Church as an article of faith, thereby greatly discouraging scientific inquiry. Putting the Earth in the center was seen as consistent with the idea of creation in Genesis. And because of this, and probably because of other trends that were going on in societies at this time, in the Roman Empire certainly, and later, it became frozen in place. But being frozen in place, being understood to be the explanation, undoubtedly helped to provide some certainty to the people who lived in those times. But there were other individuals who had learned things, people who had contributed greatly, and I want to touch on them. These things eventually, some of them, would come back to make it difficult for the geocentric theory to stay as an accepted idea. That and the telescope, certainly. Aristarchus of Samos. I've identified his life as about 300 BCE. That was right after the death of Aristotle. And again, that's close to Miletus. His method of determining the relative distance from the Earth to the Moon and to the Sun. Now, if you think about the Moon going around the Earth, when it's in the direction of the Sun, we're looking at the dark side of the Moon. We call that new moon. And it moves in a counterclockwise sense if we're looking down the North Pole, whether you're a geocentrist or heliocentrist. And if the Sun is infinitely far away, then this angle is going to be 90 degrees when the Moon is seen as half lit, what we call first quarter phase. But if it's not infinitely distant, the angle can't be 90 degrees. And Aristarchus made an effort to measure it. Very difficult to do, because how can you be certain of the moment when it's half lit? It's tough. That's part of the difficulty. And then measuring the angle properly. He got 87 degrees. Now that what he may have been doing is setting a lower limit on the angle. But today we take a look at it, and it's almost 90 degrees, just a little bit less. And what the results suggest is that the sun is about 19 times as far away as the moon. And it's a whole lot further away than that. But with that, he can take the additional bit of information that both the sun and the moon fill up the same angle in the sky. Think of a solar eclipse. The moon just barely covers the sun. So if the sun's much further away, 19 times as far away, it must be 19 times as big across. The result not only says that, but it also says the sun is bigger than Earth. And with that in mind, Aristarchus suggests that it's the sun that's at the center. How can something bigger than Earth go around the Earth? And he also suggests that the universe is much bigger than it had been thought of. Now, there was a test for this. You could watch the stars, see if a close star, look for close stars. And if one of the stars seemed to change direction over the course of 6 months, that would be evidence that it was, well, that Earth was moving. But it could be seen. The reason we now know is the stars were too far away. They still are too far away. Not just in the past tense. But to the Greeks, they could see no reason to adopt the heliocentric model. Now, Eratosthenes was librarian. I have to mention the librarian in here. He was chief librarian of the Library of Alexandria. And he learned that in the town of Syene, which was far south along the Nile, up the Nile, because it flows to the north, on the first day of summer, the sun is straight overhead. Tall poles cast no shadows, and the sunlight went right down to the bottom of a well. But in Alexandria, where he was, the sun was not at the point straight overhead, the zenith. It was 7 degrees away. And he sketched it out something like this and realized that he had a tool to figure out something very important. He had a distance known or found out or surveyed or estimated between Syene and Alexandria, and from that, well, that must be 7/360th of the circumference of the Earth. And hence came up with a value for the circumference of the Earth that, by some accounts, was correct within 1%. By some accounts. Not sure which unit he was using. There were too many stadium units by this time, the length of the Olympic Stadium in Greece. So he might have been off by more, but giving him credit for the best possible, he had the best estimate of any. Looked like Posidonius did quite well too, but I'm not sure that's right. But Eratosthenes was very close to the true circumference of the Earth, what we now measure. And so when Columbus set sail, and that would have been 17 centuries later, it's not a question of whether the Earth is flat. Excuse me, it just bit my tongue. Not good. It's not a question of whether the Earth is flat. It's a question of just how far he can sail safely. Can he carry enough provisions? Hipparchus is considered by many to be the greatest astronomer of antiquity, and certainly for his observational prowess. If you look into the northern sky, you will see, and let me try to block and shade this a little bit. No, I'm not wide enough, have to have more pizza. Thank you to the Astronomy Club for last night, by the way. But we've got Polaris and Ursa Minor, the Little Dipper, and we've got the Big Dipper over here as part of the Great Bear, and we've got Cassiopeia, the Queen of Ethiopia over here, and many other star patterns that have been named by the Greeks and civilizations before them as well. And Polaris is almost directly overhead the North Pole of the Earth, so it doesn't move much. It helps us find our way if we have forgotten to take our GPS with us. And looking again at that slide I showed you before, you see one star close to the center that does leave a little trail. It's a bit brighter than any others in the vicinity. That is the star Polaris, the North Star. Hipparchus saw a nova, saw a new star appear in the sky, and it angered him. Not seeing it, but that when he went to the star charts, he couldn't tell. They weren't good enough to be able to tell if this was really a new star. So he started plotting out stars on a new chart, new map of the sky, so that future individuals who, if they saw a new star, would be able to tell, was that star there before or not? And when he did this, he had a chance to check and compare it with another map that had been drawn centuries before, and lo and behold, the point in the sky about which everything was turning was a different point. The sky was precessing. The North Celestial Pole is moving. Today, it's right by Polaris. In 3000 BC, we now know it was by the star Thuban in Draco, and that's 5,000 years of time. So maybe take half of that, 2,500 years, a little bit less than that. Right down in here was the point that the sky was turning about back in Hipparchus' day. He was able to find out that the Earth's axis is wobbling. It's like a top that you spin on the kitchen table or kitchen floor. And not only does it rotate, but it also, the axis does this. Well, the Earth is a spinning top. He didn't know that that's what's going on, but that's what it was. And 26,000 years, very slow movement. That much time will be required to bring the North pole of the sky back to the same spot. He had a method of measuring the distance to the moon as well. That wasn't mentioned on that drawing before, but he had a different method. I want to close with this quote from Carlo Rovelli. I've quoted him quite a bit. Again, it's a book I would recommend reading. Science, above all, is a passionate search for always newer ways to conceive the world. Its strength lies not in the certainties it reaches, but in a radical awareness of the vastness of our ignorance. This awareness allows us to go on questioning what we think we know and have learned, and thus to continue learning. Not certainty, but a radical lack of certainty nourishes the search for knowledge. It's not the same rock as an ardent belief in a religious text, but there's no reason one can't have a belief in a religious text and a love of science. There's so much that we have to learn. There's a whole lot to be learned 26 centuries ago. There's still a lot to be learned now. We keep finding that every idea that gets accepted eventually gets knocked off the pedestal. And that is my contribution here. Thank you. Just gorgeous statues. Pegasus, the winged horse, I've had one group out that I've had a chance to show that to. That star pattern, at least, not the flying horse itself. You have to use your imagination that's what it outlines in the sky. But there it is. Nice sculpture. And if you look carefully, right up here, you'll see a baby flying off in the distance. Baby winged horse. So there was also Poseidon in Florence. And what else did we have? Buonvenuto Cellini's bronze of Perseus and the head of Medusa. And we have Perseus the warrior in the sky close to Cassiopeia, and also to Andromeda. and Pegasus. Um, Reminders of the Trojan War. That was probably fought somewhere, Lee, can you give me a date? Maybe 1200 BC?
There was no actual Trojan
There was no actual Trojan War. I read Homer's
Circa 1200.
circa 1200. Okay, but certainly reminders. I thought that was evidence in behalf of that. After Florence, moving a little closer to Greece, went to the other side of Italy, and on the Grand Canal in Venice, looking over at St. Mark's Cathedral. The cathedral right here, this building, the Campanile, or bell tower, and we'll go up that. It's quite
behind the screens and the curtains. We want to acknowledge him, and Arlene here will give him this certificate of appreciation, working behind the scenes, but always seen.
Oh, well, thank you so much. Thank you for
Thank you. Thank you. Another thank you goes to Bev. She faithfully documents in picture, artistic picture, all this symposium and other stuff. You have seen her. Maybe in your graduation you'll see her also. She'll take your photos as well. So thanks, Bev. Thanks to Wes, also documenting in video. So thanks to all the media. Please give them a hand. Without this, we couldn't document it. Well, he tries to bring the skies down to earth. And he is a down-to-earth person. I mean, I've never seen such a pleasant person to talk to and discuss things and work with over the emails for a long time. And then when I met the person, it was a pleasant surprise. So thank you very much for accepting to come and speak with
thank
us.
you, Wafik. So, I
You
should
are
start?
all
Okay,
yours.
very good.
All yours.
Thank you.
Thank you.
Well, let's get going. I've got title slide here with a couple of graphics. A year ago, the title was Bringing the Sky Down to Earth. That was Egyptian astronomy. Here we're doing it a little bit differently. Astronomy in ancient Greece, that's not where it started. That's not where we began seeing astronomy, but I think that's where it became a science.
Well, good afternoon. And you can't find a better day with sunny sky in November. Believe it or not, it is the 1st of November. And we are thankful for the good weather. And our thoughts go for sandy people on the other side of the continent where they have some troubles. So we just count our blessings here and pray for them and bring them in keep them in our thoughts. Welcome to this session, special session of this symposium, a futuristic look through ancient lenses. Now, if you are in a class with Mr. Linton, you are obliged to look into the skies, kind of. You have to, because this is your work, your study, your specialty. But guess what? We, the 21st century guys and girls, mostly lost the glory of looking to the skies and have our thoughts just go and float like this. I wish many more would do this and look at the moon, look at the stars, and so forth. Well, before I introduce our distinguished speaker today, I want to thank John Luby and give him a hand, please. Now, if you see microphones and media services and others, usually you don't see the people.
A view from up there, go up there in a moment. You have this building that we're going to take a much closer look at here shortly. This is a building with, a clock in it, very special clock that we'll take a look at. Let's go to the top. And when we go to the top, we find Galileo again. He has been here, and he was there. Well, this is 2010 when I was there, so just over 400 years ago, and it was August 21st that he was there, and what was he doing? He was showing off the new telescope, a telescope that he had built, to the leader of Venice. And he's trying to sell it and sell himself as the maker of the telescope. He did not invent the telescope. He heard about it. And with the glassworks near Venice at Murano Island, he was able to get glass ground to his specifications and to make telescopes. He made some money doing that. He got some influence and a great reputation. 1609, August. And what would you use a telescope from up there for? He's not looking very high in the sky. In fact, I don't think he should really be looking up at all, because when you look out, you're looking down at the red tile roofs of Venice, and off in the distance, if you're looking in the right direction, you're looking towards the Adriatic Sea. Maybe there's some enemy ships coming in. You can see those. You can use this for defense, early warning device. And that science, or maybe not exactly a science as we define it today. There weren't all the elements of science going on then, but many aspects were created, invented in ancient Greece. On the the left side of this screen, you have a depiction of the Pythagorean universe, the central fire, the hearth of the universe, the home of Zeus. It's been called all of those. I will talk about that a bit later. We can't see it because there's a counter-Earth there between us and the central fire. That was one of the models. Hipparchus, a person that I also have not spoken of in the astronomy classes this semester, is probably regarded as the greatest astronomer of antiquity. You'll hear some about him yet later in this in the semester, those of you who are in my class. You see him there actually observing with an instrument known as a quadrant, astrolabe perhaps, measuring perhaps the altitude of a star, perhaps measuring something else in the sky. So Greece is a long ways away. So on our way to Greece, let's stop off in Florence. And we did so 2 years ago. I didn't know in advance that you were going to be doing this, but met my namesake, hobnobbed with some ancient astronomers, and had a feeling, as I've looked back through my slides, I've had a feeling that maybe I really was in Greece. There was statuary.